in this example, I would like to show you how to calculate the hyperfine structure of the hydrogen atom using the package QM-Maxima. So to begin, we'll again load the QM package, which is with this command, and then also load wx.lisp because we are using the wx-maxima. Now, the hyperfine splitting in hydrogen is due to the spin-spin interaction of the electron and the proton. And you can write the Hamiltonian, the interaction Hamiltonian, as 2 times A, which is some amplitude, divided by h bar squared, times the S1 dot S2, where S1 is the spin operator for particle 1 and S2 is the spin operator for particle 2. Now, in QM-Maxima, we remember that the S operators are reserved for matrix representation of kets that have a matrix representation, but here we don't have that. We're going to use JM kets for this, and so we have to use the J operators instead of the S operators here. So we can, this S1, 2 times S1 dot S2 can be written in terms of the latter operators, J1 plus 2 minus and J1 minus 2 plus, and then J1z times J2z. So we can rewrite the Hamiltonian, and we'll rewrite it in the form that's shown here. And when we do this calculation, we want to make sure we declare any symbols here as scalar, if they are indeed scalar, so that they will be handled appropriately by the Maxima code. So if we do that, we have defined our Hamiltonian, and it's shown here, and we're going to use the basis set that's predefined. So this is automatically loaded when you load the QM package. And this stands for basis set in the J representation, and it's 2 spin 1/2 particles, so it's B, J, 1/2, 1/2, or 1, 2, 1, 2. And you can see here what the basis looks like. So we have 2 particles in the spin up state. It's the first element of this list. And the second element is a tensor product where I've got the first particle in the up state, second particles in the down state. The third slot here has the first particle in the down state, second particle in the up state, and then finally both particles in the down state. So that's our basis set. And now we can calculate very simply the matrix representation of our Hamiltonian by using the matrix representation, or matrep function. So the first slot goes the Hamiltonian, and in the second slot goes the basis set that you're using, that you want the representation in. And so it gets computed and shown here as this the following matrix. Now we can calculate the eigenvalues and eigenvectors by just using this particular matrix representation. And that's shown in this line. And you can see that we have one, so the eigenvalues are in the first list here, and the eigenvectors are in the second list. In the first list, you see that we have a degeneracy here of 1 for the state with minus 3a over 2 in energy, and then we have a triply degenerate state with energy a over 2. And then corresponding to those eigenvalues of the matrix are the eigenvectors. And so you can see here that there's a list that contains, so there's, first of all, there's a big list here, and that list contains 2 elements, each of which are lists. The first list is corresponds to the this one singly degenerate element here, and then we have, for the triply degenerate element, we have 3 eigenvectors shown here. That is the second list in this overall list. So we can reconstruct then, in terms of our original basis states, we can reconstruct the stationary states of this Hamiltonian from the results that we get from the output of eigenvectors. And so we can do that here by using the function stationary. So in stationary, we input both the evals, or eigenvalues, and the eigenvectors, because we input the eigenvalues here because we need to know their degeneracy, and which eigenvectors go with which eigenvalues. And again, we have to input the basis. So when we do this, then we are left with the following stationary states for the Hamiltonian. So the first one here is an admixture of the basis sets 2 and 3 with a -1 sign for the second tensor product ket. So the first element of our list here in our stationary states is the sum of 2 tensor product kets, this one with a -1 overall common factor. And then the next state is just it's only one of the eigenvectors. It's the very first eigenvector, and that's listed here with 2 particles in the up state. And then the middle one here is an admixture of 2 tensor product states again. And then the final state is just the last tensor product state that had both particles down. Okay, so now the singlet state is the state that only has a single eigenvalue, and then the triplet states are the states that have the triplet states have the degenerate eigenvalues. So we can look at the total z projection here for each of the states. So these are for the singlet state, the total spin, or the spin projection, is 0. For the triplet states, we have one that has a spin, a z projection of 1, one that has a z projection of 0, and then finally the last one has a z projection of -1. And that is how you can compute the hyperfine splitting of hydrogen using the QM package.